All right. Hi, everybody. This is our first lecture on physics and society. And this one is going to focus on people and energy. So it's a little bit of an introduction and then a little bit about people and energy. So here we go. So the main goal of this physics and society unit is going to be to understand what energy is. So it's kind of building on our last unit, where the world's energy comes from, and then also what the impacts of its use are in order to be able to assess scientific arguments as well as claims which are not based on science. Basically, as you go out into the world, right, there's going to be lots of claims related to climate change, related to the way that we use energy, just related to science in general. And it's important that we kind of take a look at, are we able to look at that and make sense of that in some way, and be able to determine whether that's an accurate or inaccurate claim. So, why would we study this, right? So, we are and have been in what is called an energy crisis. Um, there are big decisions that are being made and need to be made, about energy use, about climate change. And it's important to be able to understand what's going on. Again, partly because then you can make, right, understand claims and correct claims, and so help us make the best decisions possible. It's also important because you pay for energy, like you will use and pay for energy throughout your lifetime. And the more you understand about that, the better, the better decisions you can make, the better, um, the more you understand about the system that you live in, the better. So, um, skills that'll come along the way or that we'll learn. Right, we're actually going to do quite a few, mostly in the lectures, quantitative assessments and in the homework as well. Meaning that, or estimates, sorry. Meaning that basically quantitative just means with numbers. So we'll be making estimates about particular things, uh, and so just getting better, kind of off the cuff, um, you know, estimates of things. Um, right, we're gonna be interpreting graphs. Right? In this class, we've been really focused on just like motion graphs or force versus time graphs or something like that. And these are going to be very different graphs. They're going to vary a lot because we're going to be looking at a lot of different things. Population, energy usage, climate, like all these different things. And so, being able to look at a graph and interpret that is going to be a skill that we're going to use and improve. We're also going to ask the question of how do we know things, right? And again, this goes back to the claim thing as well. Like, um, when we look at something, like how do we know that that is true when it comes to people, climate, energy usage, like being able to ask that question and go back, and figure it out is an important skill to have. So there you go. Okay, so if you read chapter one, it's all about energy, climate, and population and how they're all related. um this slide is not quite done, obviously. The first chapter goes over global energy flow, so it's got bits about like how the energy comes into the earth, how it leaves the earth, and it's also about how human populations have affected our energy use. Like, obviously, I not continue that statement, but it's about like um, how like how the population and population growth have affected how much energy we use, um, and like how we use that energy. Um, so that's kind of an introduction to that. Um, so first up, like we spent a whole unit talking about energy. So we know that without it, nothing happens. It's the ability to, right, do work, or, right, the ability to do something. If you want stuff that's in stuff that allows us to do stuff with other stuff. If you remember back to our definition of energy. So the first tactic is just to refresh our energy of language, or our language of energy. Right. Going back, we're going to be talking about watts. We're going to talk about joules, like that kind of thing. We're going to use our basic mathematics of energy, and basic quantitative estimates. So you'll see that later in the presentation here. Um, But we're actually going to talk mostly about watts, about power, the rate of energy use. So, especially or today at least. So, um, yeah, and also that you could then explain these ideas to your these ideas of energy to your friends and family, right? Like as you learn this stuff, that you can use that language and be able to then explain it to somebody else. Meaning that you can take our scientific language and kind of convert it into something that somebody that's maybe not studying physics understands. So, like, just refresh your memory. What forms do you know? So go back and pause the video right now. Go back, think about like what types of energy do you remember from our energy unit? What ones do you know? And they could be like ones that we've learned a lot about, or ones that you remember we talked about right at the beginning of the unit. But I'm hoping you can come up with at least three, but maybe more. So pause, do that, and then come back. All right. So now that you're back, and you've taken a moment to refresh your memory of some of the types, um, let's take a look. So these are probably the ones that you remembered, right? Kinetic, elastic, gravitational ones. Those are ones we've talked about and learned about a lot in our energy unit. Hopefully, you remembered those. There are other ones that we didn't really talk about, but they're going to be important in this unit. There's thermal energy. Thermal energy is heat energy. Um, So if something is hot, it's going to have thermal energy. Um, Chemical energy is the energy stored in molecular bonds, which is usually like something that you can burn, um, right? So, you know, oxygen and carbon, those can be turned into carbon dioxide. You know, hydrogen and oxygen, those can be burned to turn into H2O, water. Um, so just things like that. Those are like the most common ones. But any basically, if you have a chemical reaction happening, um, that would be, and I guess I'm using the word burn there kind of loosely. That could be energy that's released by combining or splitting chemical bonds. So, um, you know, gasoline is another right, a very common example of coal, those kind of things. We also have nuclear ones. That's energy stored in atomic bonds. Don't know if you call it atomic bonds, but um, anyway, um, basically, if you have a nuclear reaction happening, so if you're taking one atom and you're combining it with another atom to get a whole brand new atom, then then that would be an example of a nuclear, basically a nuclear reaction. Um, so anytime that's happening and you're getting energy out, that would be nuclear energy. So those ones are ones that are going to start to come up that we didn't talk about in our last unit that we are going to talk about now. Reminder for you about conservation of energy and energy transformations. I didn't really use the word energy transformations very much, but it's just energy being transformed from one thing to another. Um, Remember that energy cannot be destroyed, only change from one form to a different form. So, from gravitational energy to kinetic energy as you drop something, right? And so that kind of idea, or elastic energy to kinetic energy as you release a spring. So we can't destroy energy. Energy all like right, it's going to exist. So it can only change from one form to another. And we can say we lose energy, but generally what we mean by that is that energy is becoming thermal energy. So again, not destroying it, it's just becoming thermal energy, which is difficult to transform into other types of energy. Some examples of energy transformations that would apply to this new unit that didn't apply, or that weren't really in our last unit, would be like, let's say you are burning something, a fire, right? Fire is going to be changing chemical energy into thermal energy, right? And meaning chemical energy into heat. Chemical being the energy stored in the in the log or whatever you're burning. A car is going to change chemical energy in the form of gasoline Into kinetic because the car is moving, and thermal energy because the engine is hot. In fact, right, a lot of the, like at least half or more of the energy is being converted into thermal energy. Um, right, like dams are going to take gravitational energy. That would be the energy stored in the water behind the dam, right? Because if you had your dam here, right, you have all this water up here, and basically you let it go right to down there. That's stored gravitational energy. You can right we convert that into almost almost any other form that may be nuclear, meaning that we turn it into electricity, and then from electricity you can turn it into kind of basically whatever you want, just about. Um, except it probably not nuclear. Um, so then let's take a car for example. Car's moving, so it's got a lot of kinetic energy. Let's remember that's it's 1 half mv squared for kinetic energy. It's got a lot of mass, it's got a lot of velocity. You step on the brakes, and in the energy unit, we just said, oh, like the work, there's work, negative work, and it's gone, right? But we never actually talked about where did it go. Um, and so, like when you step on your brakes, for those of you that are not into cars or know very much about cars, right? You have a basically your brake consists of a little rotor, and then it's got a little brake pad there. And the brake pad squeezes down on the brake rotor, so it kind of clamps it. So from a front view, I suppose you have your brake pads, and they push against each other there. And so basically, what a car is doing is it's changing all of its kinetic energy. Um, right, our equation we called it work in our last unit, but right, that work would take the form of thermal energy, because there's friction there. That friction is basically just turning, you know, kinetic energy into heat, heating up that brake rotor. Um, and so that's kind of where all that energy goes. Just another example of, now we do care about thermal energy. So just an example of like where that energy goes and kind of taking that conversation slightly further. So all this energy that we use, that we've been, like if you just think through your life and all the energy that you use throughout the day to like, in your house to, your lights, your cell phones, your heaters, your car with the gasoline, like um, all of that, the food that you eat, where does all that energy come from? Like where's like how can we trace that back? And because you can take any particular thing and you can actually trace it back to, like, let's just say you ate breakfast this morning, right? Perhaps that breakfast is, like just let's say cereal or something like that. Cereal is a grain grew in a field um, because of photosynthesis, so that energy came from the sun. Or maybe um, maybe the heat in your house is made of, is natural gas, right? That natural gas came from, you know, fossil fuels that are in the ground, which came from old plants, which are fossil, right? Which are photosynthesis, which came from the sun. Or let's say that your lights are running on electricity that came from a dam. That dam, the water, right? The electricity for the dam came from the water that's behind it. The water that came from there was evaporation, which, right, came from water that was evaporated and then rained, which would be an example of right, so it got up there because of energy from the sun, which caused the evaporation. So basically, um, any energy we talk about can get traced back to the sun. Basically, the energy coming from the sun, and like if we kind of trace this through, most of the energy or a lot of the energy is actually reflected, either like off of water or snow or ice or something like that. Um, but about 2/3 of it, or a little over 2/3 of it, is absorbed by the Earth. And right, the sunshine hits the Earth, Earth warms up, and so a lot of it turns into heat, basically. Um, just heating up the air, that kind of thing, and thus turning it into thermal energy, which is sent back into space. So you have basically infrared radiation, which is trying to get back out through the atmosphere back into space. Um, so a lot of that energy is also turned into evaporation, right? I was just talking about that, but if you think about like let's say you try to boil off like a pot of water on your stove, think about how long you have to, how much energy you have to put in to to basically evaporate that water. It takes quite a bit of energy to evaporate water. So a lot of that solar energy is going into evaporating things. Like just think about like it rains and then a while later, like it's all evaporated. That took quite a bit of energy to like evaporate your mud puddle or something like that. So um, again, that's still thermal energy. Right, uneven heating of things, that's going to cause wind currents, and right, you end up having a lower density of air in some place because it got heated up and rose up, and so therefore that makes the wind blow. So the sun is making the wind blow. You have only about 0.08% of it is turning into plants. Plants are eaten by animals. Again, turning into thermal energy. Eventually, right, if you wait long enough, those plants are going to turn and animals are going to turn into fossil fuels, right? And of that fossil fuels, right, we only use like about 0.07007 of that is actually used for human uses. So let's see here. So human or nuclear fuels, we also use some nuclear fuels there. And so that goes into human uses. So like in general, compared to the amount of energy that's coming into the sun, we're using about 0.008% of that. Um, for whatever we're to try to power our Earth. So like, but that's because the sun is putting in a tremendous amount of energy. But right, if you look at the where our energy is coming from, most of it is between fossil fuels and nuclear fuels, right? So I mean, yes, we do have wind turbines, we do have solar panels, but like it's just such a small amount that it doesn't even impact it at this point. We do have motion of the Earth and right, so that's going to create and moon. That's going to create tidal energy, making the tides up and down. We also have energy in Earth's interior, right? The middle of the Earth is very hot, um, and that's going to be releasing thermal energy, maybe in volcanoes or something to that effect. Um, and so that's releasing a substantial amount of thermal energy as well. So right, we have for fuel flow or energy flow versus fuel. A flow is a stream of energy that arrives at Earth more or less at a steady rate, versus a fuel that is stored in some way. So, right, the sun is an example of an energy flow because it's always coming in, and fuel would be an example of, or sorry, like fossil fuels or nuclear energy are examples of a fuel which is stored in some way. Okay, so real quick, right, just to do a little problem solving here, right? We said one of our goals is to get better at doing some estimates and things like that. So it says if the energy arriving at Earth is at a rate of this, there's actually we could do. There's a problem in the book we could do the calculation, but I'm just going to give you that. So it's not too difficult. Just figuring out this number came from basically figuring out the intensity of the sun, figuring out the cross section of the sun or the Earth, and figuring out how much energy per second the Earth receives. Um, so a lot of watts there, right? That would be, remember, watts are joules per second. So it's a rate, it's the amount of energy per second that the Earth receives. This is how many watts of fossil fuels are used. So if we go back, right, we use about 0.007% of fossil fuels. Um, and so let's actually go ahead and use the 0.008% one. Just we'll throw in the nuclear fuels in there as well. Just to maybe talk about how much how much human uses. Um, so how many watts of fossil fuels? Because it's mostly fuel or fossil fuels as opposed to nuclear anyway. So, but we'll throw the nuclear in there as well. How many watts of fossil fuels are used? So that's just right. It's pretty easy percentage to take. We just need to find about 0.008% of that number of the 1.78 times 10 to the 17. So take your 1.78 times by 10 to the 17 times by, right, so 0.008%. Remember that you have to move the decimal point 2 places. So you want the decimal that you're going to multiply by is that, right? So just remember that if you wanted like 10% of something, you multiply by point zero, whoops, um, by 0.1, right? Why? Because you move the decimal point uh, two places. So, um, so we're going to multiply by 0.0008, and that's going to give us 1.42 times by 10 to the 13 watts. So that's how many watts of energy we're using. Well, or yeah, right? So the number of that many joules per second that society in general is using. And that's generally in the form of either, right, of burning something, whether it be your car, whether it be a natural gas power plant, whether it be, um, you know, what was I think, a nuclear power plant, like so that's how many watts of fuel and nuclear power we're using per second, or how many joules. How many watt or how many 100-watt light bulbs could be lit with that much power, right? So we don't even really use 100-watt light bulbs anymore, but a 100-watt light bulb is like very bright, and it would be using a pretty substantial amount of power for a light bulb. But right, pretty easy calculation to figure out how many light bulbs you need. You just take your 1.42 times by 10 to the 13 watts and divide by 100-watt light bulb to see how many light bulbs it takes. Um, and of course, that just moves the decimal point a little bit. So that's 1.42 times by 10 to the 11 light bulbs. So, um, okay, so if you look up on Google how many people, what the population of the world is right now, we're at 7.8 billion people approximately, right? It's an estimate, of course. How many per person is that? So, meaning that like it's a way of thinking about how much energy does a person use, right? So basically we can take the number of 1.42 times by 10 to the 11 light bulbs. Um, so that's how many light bulbs there are. Again, it's a way of thinking about the number of, right, how much energy you use. Divided by 7.8 billion, which 7.8 billion would be, right, billion, right, is, right, um, 9 zeros, so that would be 7.8 times by 10 to the 9 people. So that's going to give you, right, approximately 18 light bulbs per 18 bulbs per person. So that means like if you were to take, right, if everybody had 18 100-watt light bulbs going at all times, right, that would be how much energy you use, right, per person or on average. Now, the issue is that there's, right, especially here in the United States, we use a lot more than 18 bulbs worth of per person, right? Obviously, not actual light bulbs, but you're heating your house, that uses a lot of energy, right? You're driving a car, that uses a lot of energy. Maybe you're flying somewhere, that uses a lot of energy, right? So, no, are you using 18 bulbs all the time? No, but on average, a person is using as much energy as it would take to run 18 light bulbs all the time, um, spread out over across the globe. Now, there's lots of societies in other countries, right, especially third world countries, that use a lot less energy. They just don't have the means or the ability to even use that much energy, or the money. So, right, you probably use significantly more than 18 light bulbs per person. But it's just a way to think about how much energy does the average person use. Um, so real quick before we end, we just have this last slide here, relating the energy use to population and why this matters, why population is related to this as we think about global energy. That people use energy, right? So again, they use 18 light bulbs per person on average. 18, and so obviously, the more people, the more energy you need, right? So as the population goes up, each person using an approximately equivalent of 18 100-watt light bulbs, obviously that's means you're going to need more and more energy. So as our population goes up, it's growing exponentially. Um, we are going to need more and more and more energy to be able to continue to power our society. And the problem is that right since we run primarily on fossil fuels are a a set amount, a finite amount of energy, and also using fossil fuels is not good for our atmosphere, not good for our climate. Right? It's worrisome because we need more and more energy. That energy is causing climate change and it's problematic, and we have a limited supply of it. So, from many different aspects, it is a concerning problem because we are using more and more and more energy. Um, Now over the years, we have changed our farming techniques to allow us to support this population, but on the flip side, it's much more energy intense, right? We can now farm areas that we could never have farmed before by pumping water to those locations to irrigate them. Um, we have chemical fertilizers that allow us to grow right? A lot more food per acre. We have bigger tractors that allow us to farm, larger areas with just one person. But all of those things, which make us more efficient, also use more energy than like a dude with a hoe in a field, right? So, I'm not saying it's a bad thing. Just we are able to support a larger and larger population by becoming more, right by changing the way we farm, but that also requires us to use more energy to make that food. So, um, so an example is right. And this is true in many different things. This is just an example of many things have become more efficient over time. Right? We have um, we have become take, for example, cars, right? A car from 2020 is much more efficient than, a car from, the 60s or something like that, right? Cars have become much more efficient. However, right, people drive further than they drove in the 1960s. They drive, right, there are more cars. And so you know, other examples would be like light bulbs and electrical devices. Like just think about them and like our light bulbs are way more efficient than they used to be, right? Like a light bulb used to use 60 watts, an actual 60 joules per second. Now it's like five. If you have an LED bulb or something like that, much more efficient. But think about like if you ever walk into like a house that was like built in the 20s or something like that, right? It has like three light bulbs in it, or one light bulb per room. And now you walk into a more modern house and there's like five light bulbs or something like that. I mean, just giving you an example. Or light bulbs aside, just think about the number of things that you have that use electricity now, versus 20 or 30 years ago. We just didn't have that many things that used electricity. Right? We used to heat, you heat houses with like, um, like coal or a wood stove or, oil or something like that. So right now we have these like super efficient, you know, um, heat pumps, or we have these super efficient natural gas furnaces. And so like we've become much more efficient in the way that we heat a house than we used to be. However, we have much bigger houses now, or there's a lot more houses, right? So like even though we're becoming more efficient over time, ultimately our energy consumption goes up because there's just more, like there's more things, and we're also like again bigger house. Another example, our homes are right. We have much better insulation. Like they houses just weren't even insulated back in the day. Now we have like really good insulation that keeps that heat in. However, again, your house is bigger, or there's more of it, or something to that effect, right? So um, we're gonna talk more next time about like how like like different countries and like how energy changes for the type of society that you live in. So that's where we're going next. Hopefully you found this somewhat interesting, and thank you very much.